we're gonna talk about approximation algorithms again, and the method. So last time we see one paradigm, which is LP routing. Right? Today is gonna be another paradigm, which is it's called Primal-Dual method, and you'll see what it is. Yeah. So basically, from last class, you have seen two ways to design approximation algorithm. One is like ad hoc, just design something like be greedy or just try to look at the problem and try to design algorithm that makes sense. Right? Another one is this LP routing, which is just to come up with integer program, relax it to linear program, solve it to fractional solution, route it to the integral solution. So you have seen like some example of this approach already. And yeah, today is another approach, Primal-Dual. Okay. And it's going to be clearer today that from this, you really use LP as a tool of thinking, not just some powerful black box, because we just really use LP as a guide to design algorithm without calling LP solver whatsoever. Okay? And the algorithm that we get at the end is going to be fast, because usually when you call LP solver, it's like a big black box that is maybe hard to implement, takes a long time. The algorithm we see today is going to be simple to implement, fast. And this approach will be kind of not just useful for approximation algorithm, it's going to be useful for online or dynamic setting too. You'll see what I mean by online algorithm next week. Okay. So to illustrate what is Primal-Dual method, let's look at a classic problem that we have seen several times, set covers, right? I will not recall the problem too much. You have a bunch of elements, you have a bunch of sets. You want to choose a set, several sets, so that it covers all the elements. That's the problem. However, we're gonna look at the variant that is bounded frequency, which is this one. We say that it's F bounded frequency, meaning that each element is contained in at most F sets. Yeah. So basically, I fix some F, and I promised you that the degree of every element here, this is going to be at most F. Okay. And then, the goal is to find the smallest set cover with with smallest weight, total weight. That's
Is there always guaranteed to be an answer? If you're doing a bipartite graph and you're only picking nodes on the left, then I feel like I could see a situation where there isn't always an answer.
Oh, so there is always an answer because an element must be in some set. Mm-hmm. So if you pick everyone on the left, it will just cover every element.
But then if you have the constraint that an element on the right has to be contained in at most F sets, what if...
Oh, I see what you mean.
Yeah.
So it's not... Okay. What I mean here is that it's not a constraint on the solution. It's that the input is promised you. We promise that in the input, every element will be contained in not too many sets from the beginning.
Okay.
Yeah. That's clear, your understanding?
Yeah.
Good. Right. For example, when F is 2, when I promise you that each element is in at most 2 sets, what is this problem? We have seen this problem before.
Use Vertex cover.
Vertex cover. It's vertex cover. Because we think of each element as an edge. and each guy is here as a vertices. Yeah. Okay. So instead of f equals to like vertex cover, we just consider any f now. Yeah. Like f can be bigger than 2, like 10. Yeah. Okay. So yeah, like we have seen this that when f is 2, this is vertex cover. We see the 2 approximation for vertex cover. When we don't have a bound on f, we have seen log n approximation algorithm. And today we're gonna see like a simple algorithm that gives you f approximation. So it basically generalizes the vertex cover one. Okay. So so let's try now. Let me tell you what do we do when we try to solve any problem with Primal-Dual method. Okay. The first step is to come up with an LP. Actually, you can start with an IP and relax it to LP, just like before. This step is it's like last time. Okay, and I will not go through the LP again. You have seen this LP before from last time. Okay, but yeah, okay. Maybe I just say again that you have for the variable for each set, you have variable x that is non-negative, and for every element, you need that the sum of xs for all the set that contains the element is at least 1. This is like to cover each element, and we want to minimize the total weight, which is the sum of WSXS over all sets. Yeah. And yeah, we don't need to. I kind of remove the integrality constraint because I relax it. I also remove the constraint that x is at most 1 because we know that. Yeah, why can we remove this?
Because of the second constraint.
Yeah, the second constraint here.
If you have 2, you can just break it down to 1.
Exactly. Yeah. Any variable that is more than 1, you could just set it to be 1, and all the constraint is still satisfied. So only get better solution. Okay. So we just started with this LP. Okay. This is like before, but now for the Primal-Dual method, as the name suggests, you're gonna derive the dual LP. You start with like a LP relaxation, and you write down the dual. Okay. I will not go through how to derive this now. I hope you will practice. Yeah. But let me read it to you and interpret it. Okay. So we're gonna create the dual of that LP is such that you have the variable for each element, variable ye for each element e is non-negative, and for each set you want that the sum of all elements, the sum of value of ye on all elements that is in the set, this value should be at most w.
Yeah.
And then we want to maximize the sum of y. So the way that you interpret this is that it's like you kind of try to pack. You maximize ye, right? You try to put value into elements, each element as much as possible. You try to pack value ye to elements e. However, you cannot, it's like a packing. You have like a capacity for each set.
Yeah.
It's like you try to put value here. Let's say that this guy, let's say it has capacity 10. Okay. So this, and you try to put value to the elements. Maybe you put the value here to be 4, and then this is maybe 5. So this is like the capacity of this guy but the capacity of this guy is 10. So if you're gonna put some value to E2 here, now you can put at most 1.
Yeah.
To satisfy this constraint for the set S2. And you have this this capacity constraint for every set. Okay. So try to pack value into elements and you have capacity on every set. Make sense? This is the problem that this dual LP is trying to solve. Okay. Questions before I go on? Okay, so this is a step. Get an LP, look at the dual. Okay. And now is a place where you start, just write down the algorithm. I tell you how it works just for the first example, right? So the algorithm, the Primal-Dual algorithm is going to be like this. Let's say that T is your primal solution. This is like the one that you want to construct. It's like your candidate set cover. But what you're gonna do is that you're gonna maintain dual feasible solution. Why? Okay. You're gonna just introduce Y just for kind of guiding you how to construct T. Okay. And the algorithm is here. Just pick any element that is not covered yet by T. Okay. In the beginning, you can pick any elements, but once you construct T, there are some element that is not covered yet. So just pick any element not covered by T. Okay. For example, if your T is like this now, it covers a bunch of guys, then just pick some elements not covered by T yet. Okay. And for example, I pick this guy, EI. What we would do next is to increase the YE value. Like you try to pack the YE value into this element. Okay. Just keep increasing. Imagine that you keep increasing YE. And at some point, the set that contains it will be saturated. Right? Because each of the set that contain this guy, like element EI, each of the set here have some capacity. So if you keep increasing the value Y of this EI, then some of the set will be tight, will be saturated. So increasing YE until the dual constraint of some set S is tight. Meaning that this constraint here is now tight for some set. Okay. So this is tight. It used to be this much. It used to be inequality. Now it's tight. So then let's say that the set that is tight is this one. Then you're just gonna put this set into your solution T. And then this guy will basically cover more elements, and then you go to the next loop, next iteration.
Yeah.
Okay. And you repeat this until every element is covered by T.
Yeah.
Okay. Is the algorithm clear? Yeah.
So after we saturate some set, then all of the nodes that set covers are going to be covered by T.
Yeah.
Okay.
Yeah. Once you saturate the set here, you include this guy into T. So everyone that this guy cover will be now covered, including EI.
Would another way to phrase this algorithm be you pick a random element and then find the lowest weight set that like contains that element, remove that lowest weight set, decrement the weights of all other sets that that element connects to, and then remove all elements that that set connects to, and then just like repeat.
Let me repeat, but it's not quite that. You said that just pick arbitrary element that is not covered yet,
Yeah.
and then choose the set of the lowest weight.
So yeah.
Like
But it's not quite a set of the lowest weight. We want to choose the set of smallest residual capacity, remaining capacity.
Yeah, so that's what I'm saying, lowest weight, and then you decrement the weights of the
Oh,
other
I
sets.
see.
Yeah.
Good. Thank you.
But-
Then exactly. Yeah. Then if you set the weight, it's like if you increase this, yeah. If you put this y and then decrease the capacity of each set accordingly, then exactly what you said. Yeah. Okay. Good. So you see that this algorithm is like just like a straightforward, nothing. It's really combinatorial. No, nothing complicated. Okay. We just really like introduce this dual LP just for designing the algorithm. We don't really like work with the LP itself. Like we don't like call the LP solver. Yeah. Okay. So you see that like it's clear that T is a set cover, because just keep repeating until every element is covered. It also clearly takes polynomial time. Yeah. Now let's just try to bound the approximation ratio. Okay. And my key claim is this. Claim is that the weight of the set that you choose is going to be at most f factor away from the optimal dual solution, the optimal dual LP value. This is dual LP. Okay. So the weight of the thing that we choose in primal is bounded by the dual, the optimal solution of dual times f. We will prove this soon, but like if this is true, then we are done. Why? So this is like our set T, the integral primal solution. We want to minimize this, so clearly it's like at least the optimal integral solution P int. Okay. This is what we want to bound. Okay. But then we know that like op of the IP is also at least op of LP, because this is LP relaxation. But op of LP, primal, and op of dual LP are the same by strong duality.
Yeah.
But what do we know? Like, so this is at least this is at least this. But this thing says that, okay, our primal integral solution is at most op of dual times f. So we get that this whole thing, this is f factor away, right? This is op of d. This is op of d times f.
Yeah.
This just means that this is like within factor f factor as well. Okay. So it's just enough for me to prove that this is at most f times op of d. Okay. So let's try to prove this.
Where did f come from, by the way?
We'll see in the analysis in the proof soon. Yeah.
Okay.
So W of T is the solution for the algorithm.
Yeah, the solution. The weight of our solution that we construct.
do we need, oh no, it's clear, okay, never mind, apologize.
Okay. So let's prove this. Okay. And the point is this. So WT is just a sum of the set in T of the US. Okay. We want to analyze this one. What do we know at all about WS? We know that it's the set whenever we put S into T.
Yep.
This is set that is tight.
Yep.
Okay. What do I mean by that? So for all S in T, S is tight, meaning that it's tight with some dual constraint. Like it's tied with the dual. Like what I mean is that it's tight. That is, the dual constraint for S is tight.
Yeah.
Dual constraint for S is tight. So we know that instead of having that for every element in S is at most WS, we have it to be equal, right? So that it means that this is just a sum of S in T and sum of elements in S YE.
Are you, could you be double counting with that double sum, or no?
No, like for each of this thing,
Yeah.
it's really literally just this thing. We know this.
Yeah, but can't some YEs be in different sets?
It can be in many sets,
Yeah.
but like we're just gonna double count them because
Okay.
this is just
That's-
equality for
This
each.
is- This is
for
where
each
the
set.
F's gonna come from, right?
Yeah,
Yeah,
exactly.
Okay.
Like we're gonna double count at most F
Yeah.
times.
Okay.
That's where F come from. Yeah. And now let's try to write this down in the easier way. I just gonna like maybe switch the order of the sum. I can write down like sum of elements, and then this is then gonna be sum of the set T such that like an E is in S. YE. Okay. So what is this? This is just, I kind of just sum YE. What is this sum? I just sum YE several times. So like I just sum YE this many times.
Yeah.
It's just I just sum the same thing this many times.
Yep.
Okay. What is this?
Most F.
It's at most F.
Yeah.
Yeah, it's like a counter set that that contain A. Yeah. This is at most F times YE. Okay. But this thing is just at most op of D.
Yeah.
Why is this? Well, first of all, like y is like is from this dual LP, and very importantly, y that we construct is feasible, right? We really like in the way that we construct our y, we make sure that we never violate any constraint. We stop once it's tight. Our y is some feasible dual solution. It's feasible. So it means that like if y is feasible, then it cannot exceed the optimal dual LP value. This is because y is feasible dual solution. This is really important. There are two important things here, that y is feasible, and next is S is tight. Okay. Because y is feasible, that's why we can say this. And without tightness here, without tightness, you would have something else, right? You would have that, you would have this, and the inequality would be like this, and nothing works. Okay. So I hope you are convinced that now like our weight, the weight of our solution is at most f times of dual. And that's once we have this, then we are done. Okay. So this gives us like f approximation.
Can you explain why the bottom of D is greater than or equal to the sum?
Right. So like if for I just mean that for any like for any y that is feasible, let's say y prime is a feasible dual solution. That is y satisfy all these constraints. Y prime, let's say it satisfy all the dual constraint, right? So it is some feasible solution, and what is op of D is just like what you get here when you try to maximize the sum of ye.
Okay.
So if this is for all dual solution, we know that the sum of y prime e for all elements is at most, yeah, let's say y star e, where y star is like it's the optimal solution.
Yeah.
And this is just op of D. Yeah. Okay. Okay. Are we good? Okay. So, yeah. So you see that when f is 2, you recall that the problem is just weighted vertex cover. And we saw like a two approximation algorithm using different approach, using LP routing from last time. Today we see that like the algorithm, the Primal-Dual algorithm for any f. Okay. So if you want to really understand what's going on, maybe you can try to interpret this algorithm for general f when f is 2. Like just try to write down your own weighted vertex cover algorithm from the Primal-Dual method. Okay. And you can try to see what is going on in graph terminology. And you see that you're gonna get some simple algorithm, much simpler than like calling some LP. Okay. Okay. Let's see another example. This is a new problem. It's called feedback vertex set. Okay. So in this problem is just another graph problem where you have a graph and each node has a weight again. Each node has weights. What we want to do is like to find some set called feedback vertex set with smallest total weight. So what do we mean by feedback vertex set? It's just like a fancy name of saying that once you remove the set from the graph, then the graph has no cycle. Okay. The graph is a forest. There's no cycle. Like in this example, if you remove this thing, then you only get like a path, right? You only get this path. So it's a forest. And it's a solution with minimum weight. And so this problem has some application in OS, like where a cycle usually means some kind of deadlock, and you kind of need to remove like some set so that you remove all the deadlocks. Anyway, what are we gonna show? What we're gonna see today is like some log n approximation algorithm. The state of the art is actually two approximation, but it's not too hard. But I will not cover it in class, and you can just read the paper. It's really short, actually. Okay. Is the problem statement clear? Okay. So let's try to solve it. Okay. So before really going to solve, let me give some observation how to simplify the problem. So first, we're gonna simplify this. That is, if you wanna remove cycle, first of all, you can just, you know that you don't need to care about vertex with degree 1. Like it's not part of your solution for sure. Any guy with degree 1, it's because they cannot be in any cycle. So you can just remove it for free, like ignore them basically, right? It's not part of your solution. Okay. So can keep deleting degree 1 vertices. Another observation is this. If you have an induced path, meaning that you have like a set of nodes here, such that every node has degree 2. Okay. This is what I mean by induced path. It's a subset that induces a path. Every guys have degree 2. Then you could just contract them into one node and replace it with the node with minimum weight on this path. Like in this path here, in this induced path. Just contract it into one node with weight 3. Why is that? Because if it is the case that any solution would like to pick a node with weight 10, then you could just pick this node with weight 3 instead. Yeah. Because any cycle that goes through the node 10, like this cycle, must go through this node 3 as well. And you could just pick this node 3 with smaller weights. Okay. So you know that like there's no way that any of this will be in the solution. Like you can just kind of replace it with 3. Okay. Good. And then I'm gonna just keep doing this operation, like simplify the graph. Okay? And I said that the graph is simplified if I cannot prune or contract. Okay. Graph is simplified if we cannot prune or contract. And now my claim is that once you have like once you get a simplified graph that is not empty yet, this graph must have a short cycle. How short? Like 4 log n. Okay. Why is this the case? Just for a moment before I prove this statement, right? Imagine first that, assume for a moment that the graph G actually has mean degree 3. Like we know that the simplified graph have mean degree at least 2. There's no degree 1 node. But there can be still some node with degree 2, but let's say that the mean degree is even 3. Okay. Now just imagine that you just start BFS from some node S. At each step, you're gonna because the mean degree is 3, the first step has at least 3 children. Every node after that has at least 2 children because the degree is 3. So it has like one parent and at least 2 children. It might have more than 2 children, and okay. But if for each step, right? If you have no cycle, let's say I have no cycle so far, then I just keep growing this tree. There's no cycle. If I find a cycle, then I'm done. I get a cycle. But let's say I don't get any cycle, then as long as I don't get a cycle on each level, the number of vertices will double on each level because each guy have at least 2 children. Okay. But if the number of vertices double per level, how many level can that be? Well, log n. Because there are n nodes. You cannot double more than log n times.
Yep.
Okay. So you know that you must find a cycle within log n level. Right? Yeah.
I'm trying to think, just like understanding how the simplified graph would look. What would it look like if you had like a connected graph, a fully connected graph, and then you tried to simplify it?
If you get a clique, like a fully connected graph,
Yeah.
and you try to simplify it, you don't simplify anything. You don't remove anything.
Oh, sorry. Okay, so the same is saying it has a cycle less than 4 log n, not that all cycles are less than. Sorry, yeah, I was thinking in this, like obviously there's a cycle of less than that, but okay.
It contains some cycle that is short.
Yeah.
Okay. Good. So it means that, okay, maybe within log n level, you will get like maybe instead of having like this, you might get something like this.
Yeah.
And this is like log n, this is log n. So your cycle, you'll get a cycle of length at most 2 log n here. Okay. So now let's try to prove this not for the graph of mean degree 3, but for the simplified graph. Okay. Any idea why like for simplified graph you should still get something like 4 log n?
Well, if you take a non-simplified graph, let's say one that has like a really long path where it's like all degree 2, that could go on for really long, but we're getting rid of all such occurrences of really long paths. So it just makes sense that it's like there's some notion of denseness in this graph.
Right. Can we try to like yeah, that's basically correct intuition. Is there like how would you formalize this?
Is the only difference after we prune and contract, is the only difference now that we can have min degree of 2?
Yeah,
There should be no more min degree of, like min degree is 2 now.
yeah, min degree is 2.
Wait, this is how we solve the problem given this? You're asking.
Say again.
You're asking how we solve the problem now.
How like I just show you the proof, not of this thing, because I just show you the proof that if the graph has min degree 3, then there is a cycle with length 2 log n.
Yeah.
Now I asked you how to prove this one. In this graph, the min degree can be 2. Yeah, Rob?
Although like there can still be nodes with min degree 2, that node's neighbors will have more than 2 because of when we contracted. Like there's not going to be any more long paths, so like the neighbor of that node will have 3 or more.
Exactly. So yeah.
So now it can extend because of that. It should be able to extend like an additional log n factor down, right? It's like originally it was we go down and up log n, so it's 2 log n. But now when we go down, like think of worst case scenario where you have like a degree 3 or more, then degree 2, then degree 2 or more, degree 2. It's not doubling every row every time now.
Good.
It like doubles once every other time.
Exactly. Yeah. Like you used to have that like the number of vertices we need to double on every level, but now like every second level it must double because any degree 2 vertices are not adjacent to each other. So if you find some node with degree 2, then the next like it doesn't really go. It's just, this guy does okay if this node has degree 2 like this, then the next times you must double. So yeah, that's the idea. So yeah, well, once the graph is simplified, then the min degree is 2, but they are not adjacent. So every 2 level, number of vertices must double. So you cannot go on for 2 log n steps, and so your tree will have like a depth 2 log n. And at some point, you will like find a cycle, and so in total, length here is like a 4 log n. Okay. So now we kind of quite ready to do Primal-Dual algorithm. Okay. So starting point again. Write the LP. How do you write this LP? Yeah, let's try to do this because you haven't seen this LP before. So what should be the variables? Yeah.
Whether or not a vertex is removed, like an indicator variable.
Exactly. For each node, you have 0, 1 for each node. What should be the objective?
Minimize some of these variables.
Yeah, times their weight.
Exactly. Yeah. How about the constraint? Let's say that we have this. Let's say that I have this for every cycle in the set of all cycle in the graph. What do we want to write this?
Need to remove one node, right?
Yeah,
Yeah.
mean that the sum of all indicators is greater than or equals 1.
Exactly. The sum of all xv for all v in the cycle is at least 1. Yeah, that's the IP. And okay, we have IP, relax it to LP, and write the dual of that LP. So let's do that. You have this IP, relax it here, and then I write the dual. The dual looks like this. Let's interpret this again. Well, it's like a cycle packing. So you have a variable yc for each cycle. You want to pack as many cycles as you can, but you have the constraint. The constraint is that every node has capacity, and the total, like a sum of yc for all c that contains v, this sum need to respect the capacity on this node. So you pack a bunch of cycles. Like you have this node V, can pack like a bunch of cycle, but the total value of the cycle need to respect is at most like this weight, this capacity.
I don't know if this is a dumb question, but does each cycle like have a weight, or is each cycle treated equally with respect to the node?
Each cycle has some weight.
Okay, they do have a weight.
Each cycle has like the value that you choose.
Oh yeah, okay, yeah.
Like you put like value 10 into this cycle, put value
Okay, yeah.
6 to this first one. The total 10 plus 6 plus blah is need to be at most WV. And this is true for every node. Okay.
So that's like y underscore c, like c's y, like c's weight.
Yeah. This is
Okay.
y subscript c.
Oh, okay.
Yeah.
Isn't this exactly the same primal and dual as the?
It's basically the same.
Yeah, I mean,
Except
obviously like
that
different context of problem.
Yeah, it's just that I replaced C. Like it used to be elements here. Now the element is replaced by a set of, like universe is now the set of all cycle.
So could you rewrite this problem in terms of the set cover problem, or no?
Yeah. So like if you write down where like if you have you used to have set cover where this is set, this is elements, right? Now the set here is like vertices.
Yeah.
And this thing is just a set of all cycle. Then this is just the same problem, except that like there are exponentially many cycle here.
Oh.
You cannot really list out the cycle and work with that like explicitly. Yeah. So you see like it's even clearer that like this is just for helping your thinking. We don't work with this LP really. Yeah. Because this is just like exponentially large LP. Okay. And here is the algorithm. Like before, we have a primal solution. And you're gonna also have the dual solution, like that is feasible. We try to make y always feasible. Okay. And it's like, just say that if as long as the graph is not a forest yet, there is a cycle, then you need to do something. Okay. Suppose that it's not a forest, it's still a cycle, then first simplify the graph first. Okay. And then you know that there exists a cycle with that is short. So find that cycle. And this is a cycle that we can try to destroy. Okay. So what we're gonna do, we're gonna just pack the value on this into this cycle, increase yc until the dual constraint for some vertex is tight. Like you have a c, you increase yc, but like the capacity on some vertex will become tight, and let's say that node is v, so this is now tight on the node v. One is tight, then like before, we put it into your solution. So then we'll put it into your solution. So this is like, again, like you said, this is template, right? Create the primal solution only on the guy is tight with the primal constraint, with the dual constraint. Yeah. Okay. Okay. And okay, you put this guy into your solution, then you delete V. This is like now you destroy this cycle and repeat. Yeah.
Is the notion of like packing, is that a really common thing with dual solutions?
Like
In general?
there is, okay, good. It's not always the case that like dual must be about packing, but like there is the class of LP, which looks like this. It's like this is like covering. We try to cover, like you try to cover all the cycle. You try to hit all the cycle. If the problem is like covering, then the dual will be packing. And there are many problems actually that like has this flavor, packing and covering. MaxFlow is to pack path. Mean cut is to cover all the path.
Okay.
Yeah. Vertex cover this problem too is like a packing covering problem. Okay. Okay. So now, yeah, this is the algorithm. So keep deleting a node that is tight with some by some dual packing. And then once the graph become a forest, then you don't need to do anything. And then return. Okay. So it's kind of clear that this is like this gives you a feasible solution. It's like you indeed delete all the cycle because the graph become a forest. So now just need to analyze the approximation ratio. By the way, like let's at least, but okay, this is a valid algorithm, but let's at least confirm that this is actually you can implement it in polynomial time, right? Well, how like to simplify the graph, you can implement it easily. Keep deleting, contracting the guy with degree 2. How about this? How can you find this fast? Yeah.
Just BFS.
Yeah, just BFS. It's really follow from our proof. You just set a BFS from some node. Grow the tree. At some level, you will find a cycle. Just BFS. Okay. And how about this? How to increase how to like find a node with that is tight?
You know which nodes are in the cycle, so you just pick whichever one has the lowest weight. Right?
Yeah.
Lowest weight. Assuming that you're going to be decrementing weights. Like
Exactly.
what I was saying.
So think like exactly. So think like each node has you maintain the remaining capacity for each node.
Yeah.
That you can maintain. And then you look at the cycle explicitly and just scan through all the nodes. Who has the smallest remaining capacity? So pick that one. And then you pack the cycle, so you will decrease the capacity of everyone in the cycle. But the guy that you choose will become 0. The capacity is 0, and you choose that. Okay. Okay, good. And okay, then this is good. This is good. Yeah. Then everything is polynomial time.
It doesn't explicitly say it, but I assume you would also remove like if there were multiple vertices with the same remaining capacity, you would remove like all of them? Or would you leave them with capacity 0?
Let's see. We can do it. We can remove. Yeah, we can just remove all the tight guy. Yeah. Yes, good. That works. Okay. So like before, we're gonna try to prove that the solution that we choose, the total weight is at most 4 log n times the optimal dual LP value. And once we have this, then we are done. Because like before, the optimal, like our solution is at least of IP, which is at least of LP. Of LP in primal and dual are the same. And we show that we're gonna show that this is true. So this is like, everything here is factor like 4 log n away. So this thing must be within 4 log n factor too. Okay. So now we're just gonna prove this one. And how to analyze this, just like before, right? We like the only thing we know about our solution is that it's tight. Everything in our solution is tight. So we write down this is the sum of all the nodes in S WV. But WV is tight. So you don't have this, but you have this thing too. Okay. So this is for every node n here. Is a sum of all cycle that contains V, YC. Okay. And I just swap the sum overall C, and then V in S and V is in C. So what is this?
It's just the Primal
Yeah,
of all the.
exactly. Just sum the same thing again and again.
I actually gotta head out. So
Okay, yeah.
thank you.
All right. You have this. Okay. So now we're gonna try to bound this thing. Okay. Is it the case that like it's not that it's not the case like anymore that every cycle has size at most 4 log n? Like some cycle might have size really long.
Yeah.
Okay, like it's not like before that like we get some bound and just it's at most f like previously. This some cycle might be long. Okay, but the claim that I want to say that like if YC is more than 0, then you actually know that this thing is at most 4 log n. We're gonna look into this a bit later, but if this is the case, then this is just at most 4 log n YC. Because sometimes YC is 0, you don't care, but when it's non-zero, you get that this is at most 4 log n. And again, once you have this is at most of the dual. Because importantly, YC is feasible. Y is feasible. Y is feasible. We never we only increase Y until it's tight. Okay. So why this is the case? Yeah. Any ideas? Scott?
So, I mean, I don't know if this is fully thought out, but my idea is, since we're doing breadth first search, we're gonna find, I guess, I'm not necessarily guaranteed to find shorter cycles first. Never mind, actually.
Well, like, let's look at this algorithm. Which cycle do we increase the value of y?
Oh, we find a short cycle. I see. Yeah. So, I mean, I guess if we're always finding a short cycle, and then
That could cut off bigger cycles too.
yeah,
I don't know.
So this is quite intuitive in the sense that whenever we increase cy, like this cycle c is short in our current simplified graph.
Yeah.
Right. This is like the length of our cycle c.
Oh. Okay.
But also it might confuse you that actually this cycle c, it's short in the simplified graph.
Yeah.
In original graph, it can come from like a really long cycle.
Yeah.
Okay. So we need like a clear explanation why like the number of vertices in our solution can be at most log n in this cycle.
is it not what you just said, where every time we increase YC, it's only because it's in a cycle less than or equal to 4 log n, and then we take.
I'm having trouble because like if we cut, like we choose one to cut a node, that can cut other cycles too, right? Potentially, and I'm trying to figure out how to bound. Like that's how I'm thinking about it right now, but I don't know how.
Mm-hmm.
I'm not sure how many it could touch in the worst case scenario.
So, okay. So maybe I try to convince you. But the first thing is that when YC is increased, like it's more than like when we about to increase YC, you agree that like this cycle is short in the current graph,
Yes. Yeah.
right? But now this cycle is short in the current graph. Like this thing is like at most log n in current graph. Now, but it could correspond to like a super long cycle in original graph.
Yeah.
Okay. Now my question is that at the time that we try to increase YC here, could we actually have chosen any node in this cycle?
Or
No.
No.
Right.
There cannot be any node in our solution that we have chosen here at all. Why?
Because then it would still be a cycle, and all of the nodes that we took out already are like bigger than whatever min degree node we have
Yeah.
in our simplified graph.
Yeah, like if you have chosen some node into your any node in this cycle into your solution,
Yeah.
then this wouldn't be a cycle in our current graph. Because we would have like a remove this node.
Yes, where we currently.
And this cycle have been removed already.
Yes.
Okay. So before we increase this, like S intersect C is 0 before. Oh, okay. Yeah. It was like we didn't choose anyone in the cycle, even in original graph before we increase this. Okay. And like after we increase the value of YC here, there are like the only node that you can like only vertices in this simplified graph are the guy that you can choose. There are like log n many nodes here. So like in the worst case, in the future iteration, you might have chosen these guys, but there are just log n many guys here. So that's why like at the end of the day, you might choose other nodes in the cycle, but this node must be the guys in the simplified graph. But that's like log n many nodes.
Many nodes.
Make sense?
Yeah.
Right. So that's why we can bound this by log n. And now we get log n approximation algorithm. Okay. I just explained this, but yeah, not repeat. Okay. So you saw 2 examples, and I hope you get the template. This is like another way to come up with algorithm. Just first write out LP relaxation and its dual. This approach you need to have dual as well. For the LP routing, you don't need it, but this one you need LP, dual LP. And the algorithm is that you can maintain feasible dual solution. Although you don't need it, you use it for your analysis to guide you how to build the primal solution. And how do you choose any nodes or anything in like how do you update the primal variables? Well, just choose the one that correspond to tight dual constraint. So yeah, 2 things: feasible dual and primal that is tight with dual constraint. Because you choose the one that's tight, this is how you can use it to bound the primal cost in terms of dual variables. Yeah.
And when you say tied dual constraints, that's just the same thing as like adding, for example, in the first one that we looked at, like fully saturated nodes.
Yeah.
Okay.
Yeah. Like each primal variable correspond to dual constraint. So you choose a variable in primal that correspond to dual constraint, which is tight. Okay. Only choose a tight guy, and this is the reason why we can bound the whole thing. Like we have, because we choose a tight one, we have inequality here. Normally we just get this, so you would have this without tightness. This is the case in set cover. For feedback vertex set, you use the tightness here as well. Otherwise, you would have only this inequality, which gives you the wrong direction of inequality. Okay. And the punchline is that actually this Primal-Dual framework can be used to derive most of the algorithm that you might have seen. Dijkstra is actually Primal-Dual algorithm. You would actually derive this in your homework. You see that Dijkstra is just like one of the instance of this algorithmic paradigm. Even Ford-Fulkerson that you have seen is Primal-Dual algorithm too. You will not do this in your homework, but if you want to see, you can look at the link. And how to minimum spanning tree as well, and many others. Yeah. And there are many approximation algorithms out there that we will not have time to cover. Okay. Okay, let me talk about one concept that is quite important for you to be aware of, which is integrality gap. What is integrality gap? Well, let's say that you have x, which is a minimization problem, and you write down the integer program pin for x, and p is the LP relaxation. Then integrality gap is the gap between optimal integral solution and the LP, the fractional one. So you know that this is at least one, because the LP is relaxation. It can be only smaller than the integral one. You have seen at least one problem where the integrality gap is one. What is that?
Max flow.
Exactly, max flow, min cut. Yeah, that's the one where like you actually have that like fractional one and the integral one. You can route it without losing anything. But this is not the case for most problems. Okay. But the point is that we need to know, and useful to know, is that whenever we design any algorithm based on some LPP, then you know that the approximation ratio that you're gonna get is gonna be at least as bad as integrality gap. Why? Because when we try to come up with an integer solution, you get x hat. And when you design algorithm based on LP, you're gonna compare the cost of your solution here with the LP value. This is what you're gonna bound if you use, if your algorithm is based on the LPP. But then there is this gap. If the gap here between integer one and fractional one is 2, then no matter what, the quality of your solution is at least 2. Okay. So integrality gap is like the fundamental bottleneck on how good your solution can be, as long as you base yourself on this LP. Okay. Let's see some example. One sec. Okay. So let's see the vertex cover. Okay. Wait. Oh, shit. Good. Let's see like this LP for vertex cover, right? Let's try to look at what is the integrality gap of this LP, and maybe look at the complete graph. Okay. Let's say the complete graph is of size n, complete graph with n nodes.
Yeah.
What is this thing? What is this thing?
Everything's a half.
Or
for the integer solution?
Integrated solution.
So to
You
take
just take one of every. You take one guy.
No, you cannot
take
take
every-
one guy.
take every guy except for one.
You need to take everyone except
Oh,
one.
all around. Sorry,
Yeah.
sorry. I was getting confused.
Yeah. Like that. The optimal integral
Yeah.
solution is n minus 1.
Yeah.
How about the fractional one?
Everybody's a half.
Exactly.
Yeah.
Just set everyone to be like 1/2.
Yeah.
Then everything here is certified. So this is actually n over 2. So you see that like basically the gap here is basically 2. So that's basically you see that okay, you cannot hope to get better than 2 approximation based on this LP.
So does this gap always hold for vertex cover, or is this just the gap in the complete graph case?
For some graph, you can get better.
Okay.
Yeah. Let's say like for example, if the graph is a forest, you can actually show that it should be better. Yeah. Okay. And for feedback vertex set, this thing, you actually know that the gap is actually log n. Okay. How? Well, there is an example of the graph which is called Ramanujan graph. It's a graph that is really sparse and well connected, but anyway, it's going to be such that every shortest cycle have length log n. So what you can do is that you can just set the value of everyone here to be 1 over log n. So the optimal fractional value is n over log n. However, you can also show that like in this graph, the integral solution must be at least n over 4, because you can say that for any set of size 3/4 n, there must exist some cycle inside. So if you remove something like n less than n over 4, then you don't remove all the cycle. Anyway, it's just some graph that there exists some graph that exhibit the gap. But what does it mean really? It means that when you base yourself on this LP, you cannot hope to get better than log n. What we do today, you cannot get better if you use this LP. But there actually exists another algorithm that is better than log n. And it's Primal-Dual as well. So it means what? It means that if you start with some problem, you can choose different LP relaxation. Some of it will lead you to like somewhat good solution, but not best. But there is a way to choose there is not unique way to choose the good LP to capture the problem. There are better way, and it gives you better solution. Okay. So let me wrap up. So I hope you see Primal-Dual approach today. And yeah, it's super clear that this is just LP is like useful for thinking. And you're going to use this approach too in the next context of online algorithms. This is a really cool topics. This is the next theme of the rest of the class, which is how do you make decisions for the future with uncertainty? Like you don't know the future. How do you make decision that is of good quality? Okay, so yeah, see you next class.